My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about the DC motor. A motor is a device which converts electrical energy into mechanical energy. We'll learn about its idea, its mode of work, its structure, what causes its uniformity of rotation. So let's get started. The electric motor. Okay, the electric motor is a device that converts electrical energy into mechanical energy. So we obtain mechanical energy from the motor. We supply it with, electrical energy, and the device converts it into mechanical energy. So once again, it is a device that converts electrical energy into mechanical energy. And what about the idea of the motor? It is based on magnetic effect of the electric current. And also you can say it is based on the magnetic torque. Just two words, idea of the motor based on magnetic torque or magnetic effect of the electric current. And what about the structure of a simple DC motor? Of course, we've got a coil. And what about the coil? A coil made of fine insulated copper wire wound on a laminated soft iron core. And the coil hangs between two poles of a magnet. Great. And also we've got two brushes to allow the current to enter and to leave the coil. So the function of the brushes, they allow the current to enter and leave the coil. And we've got something very important, which is the commutator. What about the function of the commutator in the motor? It reverses the direction of the current each half cycle. Why? To make the coil of the motor, to make it rotate in one direction. And of course, we've got a battery. And the device converts electrical energy into mechanical energy. This was about the structure of the motor. What about mode of work of the DC motor? Starting with the horizontal position, starting with the coil in the horizontal position. When the current is first switched on, current will flow in the direction shown, direction A, B, C, D. And by applying Fleming's left-hand rule, it will be quite clear that AB will be acted upon by an upward force. Side DC will be acted upon by downward force. The two forces are equal in magnitude, opposite in direction. So they will produce a couple. And of course, a couple has a turning effect. Once again, starting from the horizontal position, and we have to start with the horizontal position. Otherwise, the device will not work. Starting with the horizontal position, when the current is first switched on, current flows from A to B to C to D. Applying Fleming left, we'll find that we've got a couple. These two forces form a couple, as I said, which cause the coil to rotate until it reaches what? The vertical position. And what happens when it reaches the vertical position? By the way, it is now shown in the horizontal position, but after rotating through 180. But let me remind you of something very important. In the vertical position, the torque equals 0. But the coil overshoots this position because of its inertia. Okay? So this is very important. Okay, as the coil rotates, as I said, the torque decreases till it becomes 0 in the vertical position. Okay? And when the coil just passes the vertical position, the two halves of the commutator is switch over and the current reverses, so the coil rotates in just one direction. Okay, and now talking about something very important, talking about increasing the power of the motor. Okay, how to increase the power of rotation of the motor? First of all, by using a set of coils. And instead of a single coil, we should use, yes, many coils, a set of coils, and instead of the single armature coil. Also, the coils are at, or they should be at equal angles together with a commutator which has a number of segments twice the number of coils. The coils are at equal angles together with a commutator split into a number of segments twice the number of the coils. Okay. Also, we increase the power of rotation by increasing the number of turns in the rotating coils, and also by winding them on a soft iron armature, soft iron core. The armature becomes, why we should have a core here, or an armature. The armature becomes magnetized and increases the strength of the magnetic field. And there is something very important. The poles of the permanent magnet should be curved. The poles of the permanent magnet are curved to produce radial magnetic flux. In this way, almost we've got the coil in the horizontal position, in the maximum position, where the torque is maximum. This means that each coil has its face parallel to the field, face plane of the coil parallel field for much of its rotation. So the couple acting on the coil is almost constant and maximum, of course. And now talking about something important, talking about uniformity of rotation. Uniformity of rotation of the coil of the motor. During rotation of the coil, a current is induced in the coil. Okay, a current is induced. So during the rotation, the motor will serve as a dynamo because the sides of the coil will cut the magnetic flux and an EMF is induced, an induced current flows. Okay, so during rotation of the coil, a current is induced in the coil of the motor. The induced current causes uniformity of rotation of coil as follows. When the coil tends to speed up, what happens when the coil tends to speed up? The rate of cutting of the magnetic flux increases, and of course EMF induced will be increased, and so does the induced current. So when the coil tends to speed up, the induced current increases and the operating current decreases, and this reduces the speed of the coil. Okay, if it tends to speed up, something will happen which will decrease the speed. As a matter of fact, it remains unchanged. So, once again, during rotation, if the coil tends to speed up, I induced will be increased, and this will be decreasing to the operating current. And when the coil tends to slow down, yes, rate of cutting decreases, EMF induced decreases, current decreases. And what about the operating current? Operating current, of course, will increase. And this increases the speed of the coil. So, as I said, battery current is constant. If the coil tends to slow down, induced current decreases, and this leads to increasing in the operating current. So the speed increases once again. Actually, it rotates with the uniform velocity, constant velocity. And now we've got some give reasons. Okay. First of all, the resistance of a conductor increases as its length increases. Give reason. The resistance of a conductor increases as its length increases. Resistance increases with increasing the length of the wire because electrons collide with an increasing number of atoms. Electrons collide with an increasing number of atoms. Also, a long wire can be regarded as a group of short wires connected in series, so the resistance is added and increase. So once again, a long wire can be regarded as a group of resistances connected in series, so their resistances are added together. Each piece of a long wire is regarded as a resistance connected in series to the rest of the wire. Another give reason. The resistance of a conductor increases as its thickness, and the thickness of the conductor decreases. We got an inverse relation between resistance and area. When area decreases, resistance increases. Okay. As the thickness of a wire decreases, there are fewer spaces between atoms and the cross-section through which electrons can travel. In addition, a thick wire can be regarded as a group of resistances, group of thin wires connected in parallel. Okay, so their equivalent or total resistance decreases. Another give reason, the resistivity of a material is regarded as a physical property. It can be considered as a physical property, characteristic physical property, but resistance cannot be regarded so. Okay, why? Yes, thank you very much. Resistivity of a material, unlike its resistance, what about resistivity? Is a constant at any given temperature. If the temperature is constant, okay, it is a constant that depends only on the material. Okay. And it is independent of the dimensions of the wire. It doesn't change when length of the wire and cross-section of the wire are changed. Okay. And what about the resistance? Resistance depends on length and area, so we cannot regard it a physical property or characteristic physical property. Another give reason, the electrical conductivity of a pure metal is high. Okay, let me say it again. Why pure metals have high conductivity or low resistivity? Give reason. We want you to explain this. Okay, simply because there are many free electrons. In metals, we've got free electrons. What does it mean, free electrons? Free electrons, they are electrons that are not bound to any particular atom within the material. So there are free electrons that are not bound to any particular atom within the material. Another give reason, in parallel electrical circuits, thicker wires are used at the ends of the battery than the wire used at the ends of each resistor. Let me say the give reason again. In parallel electrical circuits, thicker wires are used at the ends of the battery than that used at the ends of each resistor. Okay, in parallel connections, total resistance of the circuit decreases. Okay, we all agree on this. When connecting in parallel, yes, total resistance decreases. And what about the effect of this on the current, the main current through the battery? Of course, it will be increased. So in parallel connections, total resistance decreases. And the main current, the current through the battery, increases. Okay, and hence thick wires are used at the terminals of the battery. Thick wires to have, yes, low resistance to decrease the amount of heat produced, because we've got a large current, high current flows. Okay. And what about the resistances connected in parallel? Okay. But the main current divides when passing through the parallel combination, when passing through the resistance. It divides, it is split. Okay. The current through each resistance is much less than the main current. Of course, let me say it again. The current through each resistance is much less than the current through the main circuit. And this explains why thicker wires are used at the ends of the battery. They are thicker than the wire used at the ends of each resistor. Another give reason, the moving coil galvanometer cannot be used for measuring AC currents. This is very important give reason. The moving coil galvanometer cannot be used for measuring alternating current. The frequency of the alternating current is much greater than the frequency at which the coil can oscillate because of its inertia. Consequently, the galvanometer just records the average value of the alternating current. And of course, the average value of the alternating current during one cycle is 0. Okay? Another give reason, the moving coil galvanometer is provided with hair springs. Moving coil galvanometer is provided with spiral springs. So we want why we should have hair springs in the galvanometer. In other words, we want the function of the hair springs. Hair springs carry the current to and from the coil. They lead the current in and out of the coil. Once again, hair springs carry the current to and from the coil. They produce a mechanical couple which opposes the rotation of the coil. So they produce a mechanical couple which balances or counterbalances the electromagnetic couple. Okay? They produce a mechanical couple which opposes the rotation of the coil. That's to say, it counterbalances the electromagnetic couple. Also, hairsprings return the coil to its initial position, to the zero position when the current is broken. Okay? When the galvanometer is disconnected from the circuit, hairsprings return the coil to the zero position. And we've got another important give reason. The scale of the moving coil galvanometer is linear, is uniform. It is equally spaced, evenly divided. And we want to know why. Okay, this is because the poles of the permanent magnet, the magnet used, have curved, or it should have curved poles. So the poles of the permanent magnet are curved to make the flux lines radial to the core. In other words, the magnetic flux becomes uniform and is parallel to the plane of the coil. So poles of the magnet are curved to produce radial magnetic flux. Okay, and what about the radial magnetic flux? It is parallel to the plane of the coil, perpendicular to the side. Okay, so the torque is almost maximum. Okay, over the region in which the coil can swing. Consequently, the angle of deflection of the coil, theta, is proportional to the current. It depends only on the current required to be measured, and this makes the scale uniform, makes it equally spaced. Another give reason, the coil of the galvanometer is connected to a low resistance called the shunt in parallel. Why sometimes we connect the coil of the galvanometer to a small resistance in parallel? Okay. The coil of the galvanometer is connected to a very low resistance in parallel to convert it into a DC ammeter. Yes, to convert the galvanometer into DC ammeter to enable it to measure high current intensity. Function of the shunt. First of all, it increases the range of the device. What does it mean? It enables the device to measure higher current intensities. It extends the range of the device. In other words, it decreases the sensitivity of the device to enable it to measure higher current intensity. It decreases the internal resistance of the device. So another function of the shunt, it decreases the internal resistance of the device. Resistance of the emitter is less than the value of the shunt itself. So it decreases the internal resistance of the device, thus decreasing the heat produced in the device. Why? The emitter is inserted in circuits in series, so heat is proportional to the resistance, the value of the resistance. Also, still talking about the function of the shunt, most of the current entering the device, entering the emitter, flows through the shunt. and only a small fraction of the current passes through the galvanometer. So the device, the galvanometer, is not damaged, is not ruined. Another give reason, the coil of the galvanometer is connected to a high resistance in series when converting it into DC voltmeter. You know the name of the resistance, it is the multiplier. Okay, so we want to know the function of the multiplier, function of the high resistance called the multiplier. First of all, it extends the range of the device, enables it to measure higher voltages. It increases the total resistance of the device. The internal resistance of the device will be increased. So a voltmeter is very high resistance instrument because of the presence of the multiplier, which increases the internal resistance of the device. Also, this decreases the heat produced, the heat developed in the device. Why? Voltmeters are connected in parallel. Heat developed when connecting in parallel, yes, is inversely proportional to the resistance. When the resistance of the device connected in parallel increases, heat is decreased. Another give reason, a current carrying wire is placed in a magnetic field, yet it doesn't experience any force. While it carrying current and placed in a field, magnetic field, of course it must be placed parallel to the field. Force is given from the relation BIL sine theta. Therefore, if the wire is placed parallel to the field, the force will be 0 as theta 0 sine 0 is 0. Okay. Another give reason, a current carrying coil is placed in a uniform magnetic field, but no magnetic torque acts on it. It must be placed in the vertical position. Torque is given from the expression BIAN cosine alpha. Alpha is the angle between plane and magnetic flux lines. So in alpha, where alpha is the angle between plane and magnetic field, magnetic flux lines. So torque is equal to 0 when alpha is 90. This happens in the vertical position. Cosine 90 is equal to 0. That's to say, when the plane in the vertical position, the plane of the coil is perpendicular to the field. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.